Newly released images of 3I Atlas confirm it's not a comet, stunning researchers worldwide. 3I Atlas was once catalogued as a routine comet, but now it appears to be something else entirely, something that resists easy labels. The familiar signs of a comet are missing, replaced by things that raise far more questions than answers. Is this truly a natural fragment drifting between the stars? Could it be a relic from a civilization we've never known? Let's find out. When the universe started acting strange, July 1st, 2025 should have been routine. The Atlas survey in Chile spots moving objects every night. Asteroids, comets, space junk that reflect sunlight. Most get a designation number and fade into databases. But when the computers calculated 3I Atlas's speed at 130,000 mph heading straight through our solar system with surgical precision, the routine ended abruptly. The Atlas telescopes weren't expecting to make history that night. These 4 robotic sentries perched on volcanic peaks in Hawaii had been photographing the same patches of sky for years, hunting for dangerous rocks that might threaten Earth. They work like cosmic security cameras, taking pictures every few minutes and letting computers spot anything that moves against the background stars. When their software flagged this particular object, it wasn't just moving. It was screaming through space faster than anything born in our solar system should be able to travel. That velocity measurement hit the astronomy community like a cold slap. 58 km relative to the sun means this thing had been traveling between stars for potentially millions of years before stumbling into our cosmic neighborhood. Objects from our solar system don't naturally reach such extreme speeds unless something massive like Jupiter has given them a gravitational kick toward the exit. But this visitor was arriving, not leaving, and its hyperbolic trajectory told a story of origin from somewhere unimaginably distant. The statistics alone made veteran researchers double-check their math. This visitor approached within 5 degrees of the ecliptic plane with odds around 2 in 1,000. Then it lined up planetary flybys, Mars, Venus, Jupiter in sequence, with a combined probability of less than 1 in 20,000. These aren't numbers that happen by accident in a universe where random debris drifts between stars with no sense of direction or purpose. The chemical analysis came back from James Webb, showing carbon dioxide levels 8 times higher than water, a ratio so extreme it placed this object 4 standard deviations outside every other comet ever studied. But the real shock came when they mapped where all that carbon dioxide was concentrating, not randomly across the surface, but precisely on the sun-facing side. Exactly where that impossible plume was pointing. The chemistry and the physics were connected in ways that natural processes shouldn't allow. Every physics textbook says the same thing about comet tails. Solar radiation pushes dust and gas away from the sun, always away, creating those elegant streaming patterns that define these cosmic snowballs. It's been true for every single comet humanity has ever observed, from ancient Chinese records to modern space missions, until 3 Atlas decided that particular law of nature was more like a suggestion. Hubble's images from late July showed something that made seasoned astronomers stare at their screens in confusion. Instead of a tail flowing away from our star like cosmic hair in the wind, this object was actively pushing material toward the sun. Not a faint wisp that might be explained by measurement error, but a persistent focused beam of particles fighting directly against the solar wind that should have scattered them into space. When Hubble's operators first received these images, they assumed something had gone wrong with the telescope's pointing or image processing. The Wide Field Camera 3 had captured dozens of successful comet observations over the years, always showing the expected anti-sunward tails that every astronomer learns about in graduate school. But frame after frame confirmed the same impossible thing: a narrow jet of material extending from the nucleus directly toward our star, holding its shape across days of observation, like it was being controlled by invisible hands. The technical teams at the Space Telescope Science Institute ran every diagnostic they could think of. They checked the instrument calibration, verified the telescope's pointing accuracy, and compared the images to previous comet observations using identical camera settings. Everything checked out perfectly, which made the anomaly even more disturbing. This wasn't a glitch in the system or an error in data processing. It was a real object behaving in ways that challenged fundamental assumptions about how matter moves in space. The teams ran every simulation they could think of. They adjusted particle sizes, changed velocity assumptions, tweaked solar wind parameters. Nothing worked. Computer models that had successfully predicted comet behavior for decades simply refused to generate anything resembling what telescopes were actually seeing. The only way to make the numbers match required something actively launching material with enough force to overcome radiation pressure completely. The computational challenge became a nightmare for teams worldwide who tried to reverse engineer what they were seeing. Dust dynamics codes that had worked flawlessly for modeling normal comet tails suddenly produced garbage. When fed the observational parameters from 3 Atlas, the physics engines kept spitting out error messages, unable to find solutions where heavy particles could maintain stable sunward trajectories for days at a time. Even when researchers relaxed their assumptions about particle composition and allowed for materials denser than typical comet dust, the models refused to cooperate. The astrometric data started coming in from multiple observatories within weeks of discovery, and the pattern emerged slowly like a photograph developing in solution. Teams at Lowell Observatory and Gemini South logged hundreds of positional measurements, applying the same techniques they'd used successfully on countless asteroids and comets. The initial orbital solution looked normal: hyperbolic trajectory, eccentricity over 6, clearly from interstellar space. The astronomers doing this work weren't looking for anything exotic. Astrometry is usually the boring part of comet science. You measure where something is, plug the numbers into well-tested equations, and get a prediction of where it's going next. The mathematics behind orbital determination has been solid for centuries, refined through countless missions and observations until it works like clockwork. But when experienced teams at multiple observatories started getting consistent results that didn't fit the standard models, they knew they were dealing with something genuinely strange. Lowell Observatory's 4.3-meter Discovery Telescope became one of the primary tracking stations for this effort. The instrument's advanced imaging system could pinpoint 3I Atlas's position to within fractions of an arc-second, even as the object moved rapidly across the sky. Night after night, the telescope operators captured precise measurements that fed into the global network of observers, trying to nail down exactly how this visitor was moving through our solar system. Then the residuals started growing. Those tiny differences between predicted and observed positions that usually average out to measurement noise began showing a consistent bias, always in the same direction, always toward the sun. By mid-August, the pattern was undeniable. Something was continuously pushing 3 Atlas with a force of approximately 4x 10 to 7 ms2. That number might sound small, but in the context of celestial mechanics, it represents substantial continuous thrust, enough to shift the object's predicted position by thousands of kilometers over just a few weeks. The force aligned perfectly with the direction of the sunward plume, visible in every optical observation, creating direct correlation between whatever was generating the tail and measurable changes in orbital motion. To generate the observed acceleration through normal ice sublimation would require mass loss rates hundreds of times higher than what the comet's brightness suggested was actually happening. Even accounting for the weird carbon dioxide chemistry that James Webb had detected, the math didn't work. Natural outgassing simply couldn't explain both the magnitude and the precision of the measured force. NASA's Jet Propulsion Laboratory flagged the object for non-gravitational monitoring, a protocol usually reserved for unpredictable comet outbursts. Internal memos began referring to the effect as a propulsive signature, though official documentation maintained neutral language about non-gravitational perturbations. The James Webb Space Telescope's spectroscopic examination revealed chemistry so extreme it forced scientists to reconsider what constitutes normal comet composition across the galaxy. The carbon dioxide to water ratio measured 8.1, a number that places this object 4 standard deviations outside the range of every other comet ever studied by human instruments. This isn't merely unusual. It's a chemical signature completely absent from our solar system's frozen archive. When James Webb pointed its instruments at 3 Atlas in August, the science team expected to see familiar signatures: water vapor, carbon monoxide, maybe some organic compounds that had been locked in ice for millions of years. What came back through the data stream was so unexpected that multiple team members independently double-checked their calibration procedures before accepting what they were seeing. The near-infrared spectrograph on James Webb operates like a cosmic fingerprint scanner, breaking down the light coming from celestial objects into component wavelengths that reveal exactly what chemicals are present. For comets, this technique typically shows a predictable mix dominated by water vapor with smaller amounts of carbon-based compounds. But 3 Atlas flipped this expectation completely upside down. showing carbon dioxide lines so strong they overwhelmed everything else in the spectrum. Martin Cordner's team confirmed these measurements through near-infrared analysis at 3.3 astronomical units from the Sun. The carbon dioxide absorption signature at 4.3 microns overwhelmed every other spectral feature, creating readings that resembled nothing in existing astronomical databases. Even carbon monoxide, typically dominant in distant frozen bodies, registered at only 1.4 times the water content. The process of extracting these measurements required extraordinary precision and patience. Unlike bright stars or galaxies that flood telescopes with light, comets offer only faint glows that require long exposures and careful background subtraction to detect meaningful spectral lines. The James Webb team spent hours collecting photons from 3 Atlas, building up signal-to-noise ratios sufficient to measure not just the presence of different molecules, but their relative abundances with statistical confidence. The chemical distribution reveals formation history written in frozen gases. Carbon dioxide concentrates precisely on the sunward face of the nucleus, matching the exact location where the impossible plume originates. This correlation connects the object's alien chemistry directly to its rule-breaking behavior, suggesting whatever drives the mysterious tail formation operates through chemical processes foreign to our stellar neighborhood. The spatial mapping revealed something even stranger than the overall composition ratios. Instead of gases mixing uniformly as they escaped from the nucleus, carbon dioxide was streaming preferentially from the hemisphere facing our star. This kind of directional emission pattern suggests active processes rather than simple thermal sublimation, where you'd expect gases to escape more or less uniformly from the sunlit surface. Isotopic analysis adds layers to this chemical mystery through measurements of carbon-12 to carbon-13 ratios visible in infrared spectroscopy. These ratios match Earth's composition with remarkable precision, indicating formation around a star system chemically similar to our own Sun. Yet the overall composition remains completely alien to solar system norms, suggesting 3 Atlas originated in a planetary nursery with familiar stellar chemistry, but dramatically different thermal processing. The isotopic work represents some of the most technically challenging observations possible with current instruments. The carbon-13 substituted molecules produce spectral lines only slightly offset from their more common carbon-12 counterparts, requiring exceptional spectral resolution and sensitivity to detect reliably. The fact that James Webb could measure these ratios at all speaks to both the instrument's capabilities and the unusual brightness of 3I Atlas's carbon dioxide emissions. But this extraordinary chemistry doesn't exist in isolation. It appears connected to measurable forces affecting how the object moves through space. When spacecraft engineers started paying attention, the moment propulsion specialists at NASA began examining 3 Atlas's plume characteristics, uncomfortable parallels emerged with technology they knew intimately. Ion drives used for interplanetary missions work by accelerating charged particles through electromagnetic fields, creating narrow collimated exhaust streams that maintain structural integrity across vast vacuum distances. The resulting thrust is gentle but persistent, capable of changing spacecraft velocities by thousands of miles per hour over months of continuous operation. The engineers who design these systems know their exhaust signatures better than anyone. They spend years perfecting the physics of how to turn electrical energy into directed thrust, creating particle beams so precisely controlled they can nudge spacecraft along trajectories measured to the meter across billions of miles. When these same specialists looked at images of 3 Atlas, the similarities were impossible to ignore and deeply unsettling. Modern spacecraft engines work by stripping electrons from atoms of xenon gas, then accelerating the resulting ions through electric fields, reaching tens of thousands of volts. The process creates a ghostly blue glow and a whisper-quiet push that can operate continuously for months without running out of fuel. Unlike chemical rockets that produce brief bursts of enormous thrust, ion engines generate steady, precise forces that accumulate velocity changes over time through pure persistence and efficiency. The operational signature of electric propulsion has specific characteristics that make it instantly recognizable to spacecraft engineers. Exhaust particles achieve nearly identical velocities, creating focused beams that don't spread out much in space. The plume holds its shape across long distances and points precisely opposite to the desired direction of travel. In mission planning, timing becomes critical. You fire engines at optimal points in the orbit to maximize velocity changes through gravitational assists. The resemblance between 3 Atlas's behavior and spacecraft propulsion extends beyond just visual similarity. The physics of how ion engines work demands certain characteristics that match almost exactly what telescopes were observing. The exhaust must be narrow and persistent. The particles must move with uniform velocities, and the direction must remain constant over long periods. All of these requirements showed up in the observational data from this cosmic visitor. 3 Atlas demonstrated remarkably similar patterns in its documented behavior. Material jetted outward in narrow configurations, maintaining integrity across observation periods spanning weeks. The particles appeared to move with uniform velocity distributions, creating dense trails that resisted solar wind interaction in ways that mirrored ionized exhaust from spacecraft systems. Most striking was the directionality pointing toward the sun during approach, exactly what you'd expect from a deceleration maneuver. The timing aspect adds another layer of intrigue that spacecraft engineers found particularly compelling. If you were piloting something through interstellar space and wanted to slow down efficiently when you reached another star system, you'd time your burns for maximum effect using gravitational assists. The Oberth effect, named after the German physicist who first described it, mathematically allows you to multiply the efficiency of any propulsive maneuver by executing it when you're moving fastest relative to a massive body like a star. That's it for today. Let us know in the comments down below what you thought of these latest updates on 3i Atlas. Don't forget to like and subscribe for more quality content.